All right. So we are in the YakRover special session to just discuss links we've been tossing into Discord. And I'm going first with a few links that I've been posting in the inspirations thread. So this is my first selection. This guy made tiny little, it looks like a rover, but it's actually just like a little bit of wireframe with a solar panel, what looks like one capacitor, one chip, and it's this, I don't know what this chip is, ATT INI85, but it's a microcontroller, it looks like, and it talks to an LCD over I2C. That's it, it's a temperature monitor, that's it. So the prompt question I have for this is an example of an extraordinarily simple, cheap little gadget and potentially very robust because it's just no moving parts, just a few things sorted together. Potentially you could make like 1,000 such things and with a not very robust landing system, just sprinkle them over Mars, right? Like little modes. So they're not as small as the science fiction nanobots, which are too small to see. They're like not microscopic, but like palmoscopic. I don't know what the scale is called. So yeah, prompt is, what can you do with this scale and form factor? Thoughts?
Does it communicate?
It doesn't look like it. I didn't see any communication here. No, it's just got local I2C, but you could potentially do something like have a very powerful LED blinking the temperature in like, Morse code or bit code or something, and then picked up by a camera somewhere else. Or how about like NFC? If they're like tossed in close enough density, you can go to extremely low power transmission and make a little low power mesh grid to one single powerful transmitter.
If you look at the article I posted yesterday, maybe I'll share screen. A second.
Yeah, go ahead.
So it's a very, very, very small, I don't know what to call it. They call it wind dispersed something other. And it's more sophisticated. They have a temperature sensor and a light sensor and some sort of RF communication device. And look at the size. It's about 3 millimeters.
It's wild.
Okay.
Yeah, this is kind of I think the other one was more like a hobby art project. It looked like a little electronic sculpture. This one looks like a more serious like device you could actually field. Yeah, so let's use this as an example of this.
No, wait. No. Just a second. I want to say that maybe we should be focusing on the electronic sculpture part of things.
Oh, okay.
Okay, that's what I'm saying. I'm saying, people do small things, and here's from nature. They built a small wind dispersed element. You build a million, you throw them out, and they spread everywhere. They make a mesh. It's all very technological. But what you showed, can you bring it back?
Yeah, let me share this. Let me share my screen. Okay, see my screen again? Yeah, this is about palm scale.
Yeah.
And yeah, it looks like a sculpture. So yeah, what's your thought on the sculpture element?
It's not just a few pieces of metal tied together. It actually works. Okay, it's a lander, but like he says, it's solar powered. Can you enlarge the picture on the left?
The physical system is also the electronic system.
Yeah, so, I've seen this strategy.
Oh, it's got a little LCD. I see. Okay.
By the way, this idea of like using the electronic components as structural elements, I see it pop up anytime anyone wants to go extremely lightweight or form factor. Like just yesterday, I was watching a drone build video and the guy used the main power distribution board as the main structural element to even hold the drone together. And for my one of my first thoughts for the BeagleBone thing I was doing was, since it has 4 screw holes at the corners, you could just like literally attach wheel posts to the 4 and not have a chassis at all. You just need the wheel unit. So I think that's a good low cost, low weight strategy.
I think this is more than that. In other words, most of the structures from these little welded pieces of metal, but it has one function and it has a shape which appears to have nothing to do with the function, but still it's a viable device. You know, the things that I just showed was a standard, you know, compact microelectronic thing.
Mm-hmm.
This has an aesthetic to it, which is much nicer.
And you bring up an important point. Even though the particular shape may not be functional for this application, temperature is a scalar, you don't need to be in a particular orientation. Something like, say, ambient light sensor, orientation matters. If you're facing upwards, it measures something completely different than if you're facing downwards. So it would be interesting to have like and passively self-orienting mechanical structures. Like this one, obviously, this is the correct orientation up. But if you drop it in a sprinkle from like a larger spacecraft, like, 10% might land the right way up. And if you have larger rovers, they have like active mechanisms to get to the right orientation. So a good, interesting challenge would be, can you design like a passive mechanism, like maybe a parachute or like, the wind dispersed thing that you showed, something that orients it correctly, but passively?
What do you want it to look like?
Well,
does aesthetic mean anything? Because the one that I showed uses gravity and air resistance in order to orient itself.
Yeah. So aesthetics, I'm like, I don't think I'm particularly concerned with it. It's nice to have. And for other projects other than like Mars exploration, it might be a dimension I'd be interested in exploring. But yeah, for rovers, aesthetics, and aesthetics for the sake of aesthetics is not high on my list of priorities, unless it sort of serves some interesting research question. Like, is there a sort of deeper sort of philosophy behind why you like aesthetics as an element to prioritize?
In the futures that we're imagining, we're surrounded by robots. Now, one of the things which I've never actually been in Japan, but I understand is different about Japan, is public aesthetics are important. So
they aren't?
They are important.
Yeah.
As compared to other countries, and we can talk about 2 big Eastern European countries that have that problem. They're busy fighting it out, but it looks like Soviet-era building over there. So I think the question of aesthetics is very, very important because it will affect what the public space looks like. And
so sorry, it's going down a road that I'm not sure it's really solid, because culturally speaking, I think there is a there is a confusion sometimes about aesthetics and also the relationship to the environment, okay, or to nature, to be more accurate in my feeling, okay, and that's based in a lifestyle like Shintoism and stuff like that, okay. So I'm not quite sure. And here in the discussion also, I wonder whether aesthetics is the right word, because look, for something like, some movement or some shape looks like good to many people so in terms of aesthetics for several reasons, okay? And so here I'm a bit stretching, but I bet these reasons is because this is our environment. This is where we evolved, okay? And if we're talking about aesthetics on Mars, and we evaluate these aesthetics based on how life is on Earth, I don't know, it becomes very murky discussion to me and very unclear what that means, okay? Because a shape on Mars, our body on Mars, is very likely to be very different from how our body is on Earth, just because gravity is different, just because the atmosphere, there is an atmosphere on Mars, yes, they're very thin, okay? So I'm not sure whether we are talking about aesthetics or we are talking about, how to say, the fit in the local nature, the local environments. And so in Japan, okay, there are a lot of things that some rules. For example, Meyer and I, we discussed an article about zoning in Japan compared to the US. Okay, a very interesting article. So zoning is about how we structure the land. Okay, so in different kind of zones, zones where it's industrial, zones where it's residential, zones where you can have skyscrapers and so on. Okay. And so there are very different ways of doing between Japan and the US. Very interesting to, I just didn't know that. Okay, but in Japan, I'm not surprised how they do it. Basically, they put some relatively, but they have some constraints. But the point is to keep in mind that Japan is a country with a very high number of earthquakes. Okay, and so because of that environmental hazard, okay, there are a lot of aesthetics that are driven by the environment, okay, the local nature, basically. So, sorry, I feel that I'm pushing a bit too much, but I guess you see the kind of topic I'm talking about.
Yeah, I pulled up this paper, which is one of my favorites because it gets directly at this issue. So there's sort of what you described as like a cultural determinacy kind of hypothesis for why Japan has a particular attitude towards aesthetics as it does. But the more general point is aesthetics and beauty as sort of like signaling a fit between the thing and the environment. And this paper kind of has like an interesting mathematical theory that's kind of like, it's like, if you guys are familiar with algorithmic information theory, the idea of like algorithmic complexity. So an elegant algorithm. So beauty is in a sense kind of like a mathematical signal of that kind of elegance. So there's kind of like that aspect which kind of interests me. But I think I do want to like separate out what Mayer's concern is, like aesthetics as a concern for itself, as opposed to aesthetics as revealing some aspect of like evolutionary fitness, is interesting in its own right. Like I would be interested in certain conditions, like especially on Earth, of like, can we just like make robots fun and playful and beautiful to just have around us? So that might be an interesting objective. And I think there's something worth thinking about there. It's like not necessarily in a functionalist way. But I'll cede the stage for whoever wants to share their first thing next. Since Mayor already shared, maybe Eric, you or Rhett can share, and we can do as many rounds as we have time for.
Sure.
Who wants to go next?
I think. I'll move then. I have 3 articles to talk about, but I will just start with one as Venkatesh suggested. So this is the last, I think it's first I will start with the last link I shared also on Discord about an MIT team. Improving on the cheetah, the mini cheetah robot. So, okay, can you see my screen all right?
Yep.
Yeah.
Okay, so that was published last week. Okay, so the underlying paper and source code and so on are not available yet. But basically, there is a team at MIT. They have this robot cheetah. Okay, so I guess it's their version of the Boston Dynamics Spot dog. Okay. And so what they've done is that they build a specific software that makes it more robust to walk across different terrain. Okay, and they had a specific goal to try to go as fast as possible. Okay, so basically the goal of this robot is to walk, run basically as fast as possible on as many terrain as they can. Because in general, the problem with robots is that because it's related to the fact that they are very expensive to develop. But the thing is that usually we develop them for a very specific application. So it means a specific environment. It means a specific kind of terrain. Like Roombas are designed to work inside home. Okay, so on carpet or on smoother surfaces. But if you get them out, they won't work anymore. Okay, they are not adapted to work there. So here they try to deal with several environments and to have a single software that will be allowed to adapt to different terrain and still go as fast as possible. And so as fast as possible is of course vague, because maybe we can run very fast when we have a good adherence to the ground. So for example on tarmac. But on ice, as fast as possible, is going to be much slower, right? Okay. And so apparently, this robot is the robot is able to run pretty well on different scenarios. There are a number of nice pictures here and on plus videos, but also on the attached.
Yeah, Fabian just joined us.
Ah, great. Okay. Hello, Fabian. So you see they tried so indoor sprint, outdoor on the grass, spin. Oh yes, here on an ice patch. Okay, and after so on gravel and stuff like that. Okay, and so apparently the robot is able to run as fast as possible on a given terrain. It can real time adapt to the different terrain, and apparently. The paper is not available yet, I'm sorry. But apparently, if there is damage to one leg, the robot can adapt automatically and still go as fast as possible with a missing leg. Okay, and so all those concepts for me are very interesting. Okay, and so a last comment is how they do it. So they use reinforcement learning. So a specific kind. It's called a model-free reinforcement learning. Okay, so it's a technical detail. Okay, but model-free here is that they are trying to make no assumption about the kind of environment they're dealing with. Okay, which is pretty interesting because if we are looking at any organism like us, okay, in any new environment, we may not have the maximum performance at first, but it's not like we can't do anything. We can't do something. Okay. So it's one of the ideas behind what is model-free. Okay, and so that's one thing. And another last point. Sorry. Yes, there is an interesting comment from the team. Is that basically their limitation now? Okay, so of course it's a research project, so it's ongoing and so on. But for them, the next step is not about the software controller, so the reinforcement learning part, but about modifying the hardware. Okay, so the article ends with a sentence which is only the hardware is the limit. Okay? And so I found that interesting because there is this interaction between the hardware world and the software world. Okay, there is this kind of echo that we can see over time. In fact, we can see that with the CPUs and operating system is that over the years they influence each other. Okay, operating systems ask for more memory, for faster memory and stuff like that, so that will impact how the hardware is designed. And so now we have SoCs, okay, system on a chip, where we have the memory closer to the core CPU to have a faster speed and so on. Okay, and so they are back and forth for decades now. Adding cache memories, level 2 cache, and now GPUs directly attached to the SOC and so on. Okay, and so here we can see also the same kind of comment or situation appearing, and perhaps at a faster rate than before. Okay, and to finish my quick review, okay, there is interesting thing that I thought I would be impressed by the speed. Okay, and so. The thing that, according to the article, the velocity increased from 12 feet per second to a whopping 13 feet per second. Okay, and so I'm unable to evaluate. Okay, it's just as 1 more feet per second sounds like yes, an improvement. It's just I'm not sure how to evaluate the impact of that. I just believe there is potential, and I'm done saying that there is one last thing. I thought that was interesting to talk about it here today, is that model-free learning is also what Sai, I think, is doing in his research now in Germany.
Did you find any details of how they got to the 12 feet per second? Because that doesn't sound like a random motion algorithm. That sounds like it was already at a very good design baseline.
Yeah, yes, so I didn't look into it, but I had an assumption, okay? Because a lot of these research, they start with a treadmill, okay? So they have a robot walking on a treadmill, and they evaluate it like that. They measure the speed like that, basically, the baseline speed. So I would guess that's the kind of baseline they have, but I did not check that one.
I meant not the baseline performance, but the baseline controller for that performance. Like if I had to naively decide how to make a cheetah robot run, I would just do the simplistic thing of making it move in a particular gait, right leg forward, left leg back, that kind of thing. I would make up something extremely trivial and simple, and I can't imagine that would have very high performance. So clearly, if it went from 12 to 13, and 12 seems pretty fast to me, sounds like they already put some thought in the baseline control algorithm. So the reinforcement learning did not have much room to improve.
It's possible, okay. And so sorry, I don't have an answer to that question. I will look into it. It's interesting to know.
Yeah.
One thing I forgot to mention is that they've done all the improvements inside simulators first. Okay, and so that's important because there is a trend here in many research and efforts on robotics. Yes, the team simulated all the potential scenarios of the real world in a computer. So I'm not sure that's what the article says about the research. Okay, I'm not sure that all the potential scenarios of the real world are easy to simulate in a computer. But that would be interesting to see more success in doing that because it increases the feasibility to get results. Okay, it's much cheaper, and we can parallelize the thing. Okay, we can summarize years of training in much faster as long as we can add computers, basically. And I wonder whether some of the benchmark speed were not in simulators as well. Okay, it would be possible. Okay, and last is that as Venkatesh mentioned that we could first have a naive way of walking and take that as a baseline. Okay, but that would be terrible. Okay, so I wonder whether there is not a joint use of a simulation there as well, okay? because of the cost. Okay, and sorry, I don't know. The paper is not available. It's just very possible that they take an existing algorithm, okay, an algorithm for them to walk, run it in a simulator or on the real hardware with a treadmill to take a baseline, and after do their extra reinforcement learning approach to compare. Okay.
I just had one kind of thought in relation to this, which is speed is one of those interesting things where, unlike in general, I'm not a huge fan of optimization because it's it makes you fit very tightly to a particular scenario. But there are certain objective functions which kind of have like this fertile aspect where if you try to optimize them, as a side effect, you'll actually improve performance and capabilities around the envelope. So for example, if you're trying to get the fastest robot possible, chances are very high that you'll also make a very energy efficient one. Chances are that you'll make it very streamlined. So lots of other side benefits somehow seem to come out when you pick the right kind of first variable to optimize. So speed is an interesting one. Or like another similar one is like power to weight ratio. Like if you try really hard to like maximize power to weight ratio, lots of other things go in the right direction or like interestingly powerful direction. So this seems like a good thing to think about. And I wanted to connect that to the 3 laws of Robotic's discussion I led a few weeks ago, which is, I think for the first law, I said something like the rover should try to maximize its lifespan or something. So it's that kind of thing. Like, can you pick a variable where optimizing it actually makes you sort of across the envelope much more capable?
Yes, the robot will grow in skill. In fact, this is the subject of what we spoke about yesterday in our mini discussion with Fabian and Eric. And the question was, how does a robotic operating system support growing and adapting to the environment? So not all robots do it, of course. But a growing robot, we think that is one of the most important features, that it become better. It betters itself.
And it's very, very interesting about the consequences on the system design, because growing, if we look into the perspective of memory, okay? We're talking about computers, so we have a limited amount of memory on board, okay? And so what means growing here? Is growing means having more and more skills, okay? Wherever we can, I don't know how to quantify them, but more and more stuff that we put on the memory, then we have an upper limit, and it means our robot will reach its maximum at some point. But is it growing that using more memory, or is it about rewriting its software in some way? Okay, I'm not sure what I mean by that precisely, okay? But rewriting its software to be a better fit, okay? So it's growing. There is a biological analogy to that, because if we look at babies, okay, there is something called the forgetting, or the dramatic forgetting, I don't remember. It's for young children when they are 3 years old. Basically, apparently there is some neuroscience behind that. I don't know very well, huh? But they forget a lot of things they knew to do before. Okay, around 3 years old. So typically, a young child can swim. Okay, there are some countries where they give birth directly into water because the babies can swim. Okay, but after 3, a lot of babies, they can't swim anymore. They have to learn that. Okay, and so you see, it's of course the brain, the biological brain grows. Okay, so we can, I guess it grows in capacity. I'm not sure how to quantify that either. But what is important is that it changes. Okay, it's things it could do before, it can't do them anymore. So it means perhaps that the connection inside the brain that captures what we've learned, okay, changes in a way that we forget something, but to give place, to make space for something else, okay? And so I'm not sure about there is a parallel, okay? I'm not sure it's really related, but here, growing, what does it mean, okay? Is it something like that, or is it something like we just add on top on a memory like we do in any kind of computer, okay? So for an embedded system that we want autonomous in terms of mobility and energy, okay, that may be something pretty critical to be part of an operating system.
Just a quick comment. The paper I just shared, the Schmidt-Huber paper on driven by compression progress, that's actually in a way a model of what growth is. So that might be interesting to look at, because lots of sort of ideas on AI kind of come together there, like algorithmic information theory, complexity, beauty, and growth. All of them kind of come in there. Yeah, that's all I had to say.
In relation to Kadash talked about energy efficiency and improving on several matters. Okay, Fabian, what do you think about maybe talking about the ostrich robot that you talked about? We talked about very recently.
Yeah, I can do that. Let me find the link. The camera is not starting.
So sorry, Martin, I was not to shortcut you. It's related on the topic.
It's all good. I don't have anything that exciting to share.
Okay, let's get it. Let me show the screen. Okay. Yeah, this one. Yeah, this one is kind of interesting robot, because what they did here, they tried to get inspired from ostrich. So the specificity about it is really the mechanism. How to explain it well? The release mechanism of the foot part. So it's a bit similar to also when humans are running. When you run, what happens at the time of impact, part of the energy that you from your own weight, in fact, is stored in the tendon in the back of your calf, which is released for pushing you up. And I think here there is a bit of similar system, but even more complex. Maybe can I play the video? It's better. And so what they show here, so you see when they run, like there is this, yeah, that part is quite interesting. And I think they managed to reproduce it in the robot.
Definitely looks like the chicken I have outside.
Sorry?
I have a chicken outside, and it looks like the way the chicken walks.
Oh, yeah, I agree with you.
An ostrich is like a big chicken, right?
This is how you get robot velociraptors, isn't it?
Yeah. Also,
it's exercising on a treadmill.
Yeah. Here the slow motion is quite impressive. So. It's the release of the foot. So there is some kind of bistable mechanism, the tendon system that allows that. It's very interesting. And one of the benefits also is that when the robot is not moving, so it's standing straight, where is it? It managed to be stable without using any energy. Can't find it now. Right, this kind of position, which is kind of unique for bipedal robots.
It makes me think of Star Wars for some reason.
There is a two-legged robot in Star Wars also. Kind of two-legged, it's a tank robot.
Do you know, perchance, how they measure, energy efficiency and maybe how maybe they can compute what would be the minimum? Because if they're able to say that they have a system that has zero energy requirement for stable position, It means they have one way to measure what the minimum is, right?
I mean, I'm not sure if I got your question, but I would say you can simply measure the power consumption of the battery.
There are approaches in control theory that have been used for a while on this. I think they're called like you model the Hamiltonian of the system, and there's like Lyapunov function-based analysis of like at least locally you can say this is kind of an energy efficient limit cycle or gate. So there's ways to model it that it's kind of like a little bit artificial, but it tends to like I'm trying to think of there's a woman named Naomi Leonard at Princeton. I went to a talk by her a long time ago where she actually presented some results on stability theory of lowest energy natural gates or something. So I'll see if I can dig that up. But yeah, there's like principled ways you can sort of claim that gate is minimum energy in some sense. But also, yeah, just measure and compare. Like I remember watching this documentary on horse gates, and there's apparently 3 common horse gaits like trot, canter, and walk. But in England in the medieval era, they actually bred horses that could have a 4th gait called ambling. And ambling apparently is like really energy efficient over long periods. So these are like kind of interesting results that it's like it's a complex enough system that there's going to be many energy efficient like local optima, and you can actually potentially discover new ones. Like you see this in like Olympic athletes too. Like at some point in the high jump, people went from like jumping forwards to like back flipping over because it's a way to like jump more efficiently. So it's kind of like the answer is always going to be local, but in an evolutionary sense, you'll always maybe discover new equilibrium energy solutions.
Thank you.
Cool. I'll share one. I shared this a while back. That was let's see. Sai shared it with us first, and I just took some time to look at it a little deeper later. But I'm going to bring it up for a couple of reasons. One of them was kind of the answer to, or touching on something that Mayor had said he wanted. But first off, I just want to say that like, if you haven't read this through this entire like paper / website, it's really amazing just in the presentation. Like having this many like interactive diagrams and images and like all this stuff is just like, I don't know, incredible to me. So much more impressive than just a paper. But as a summary, like this whole concept that I had never heard of before of essentially having AI that dreams, and so it can train itself based on a model that has been created of the environment that it's going to live in, and that model is just purely supposed to predict what's going to happen next. So you show it a bunch of videos, and the model is going to just try to predict what the next frame is. It has a certain amount of uncertainty in it, so you get this like in the visualization, and I'm not really quite sure how this works, but in the visualization, you take the input image and the output image. If you're watching the model output, it's just like kind of this blurry, dreamlike state. And from a presentation perspective, it's just so amazing to see this like, oh, look, this is the computer dreaming. And it looks like the real world, but it's just a little blurrier. You're never quite sure what's going to happen. But then you take that model and then you can train an agent with some other objective with that model, and then it can operate at the speed of computers as opposed to the speed of whatever the actual data is that you're dealing with, and it can create new scenarios because it's probabilistic. So that connects to so many great things in here. I can't remember exactly. Oh yeah, this was awesome. Just like this is it is a road, but so it's giving you a completely different kind of experience in trying to drive. So if you can make your agent drive on roads like that, you really got something. So the idea though about seeking novelty was that you can use the same model to say, like, when the model gets the answers wrong, like it's not able to properly predict what the next frame is going to be, that can be used as a signal by the agent to be somewhere you want to go explore, because it's something, and then feed that back into the world model itself. And so it's like an iterative learning process where it can do a bunch of this like training in dreamland, but then it can also be used as a target for like what to go explore and add to its own data collection process to then dream about, you know, at night when it's not actually roving. I don't know, I thought that was a really fascinating idea, although I fully don't understand much of the details of this.
What I think is really interesting here is, you know, we get distracted by the beautiful graphics and by this idea that the rover can learn while it's sleeping. But I think what's very interesting is how we took a behavior that's only theorized to exist in people, and we're using it to make robots in practice get better. So I see this in a lot of, you know, a lot of different things use that. People say, well, people do such and such, and people do not do such and such, but people do such and such. Let's use it to make our technology better. And surprise, makes the technology better. So I'm just wondering what other examples we have of doing that.
One I can mention is from a workshop in biologically inspired control that I took long ago. It talked about research about songs in songbirds, like, you know, especially tropical islands. Mm-hmm. Apparently, they're born with some songs, but can learn other songs from like the other birds in the neighborhood. And they put, I guess, EEGs or something on these birds when they were sleeping. And it turned out that the birds were literally dreaming and rehearsing the new songs they had learned. So it looks like dreaming is actually a rehearsal and learning strategy across species for like a variety of behaviors.
On the world model, related to what I've just heard from Venkatesh, that I don't remember. I read that article, but several years ago already. So I don't remember well. But the dreaming part, is it something dynamic, or is it something that it's an analysis of the system they've built? Do you remember that, Rhett?
It is. It's not. I don't think the model is dynamic, but the way that it's explored probabilistically. So like, it gives you a range of possible outcomes, and then whatever, you know, is actually using this model can like choose one of them, and then it's like a, you know, choose your own adventure kind of thing, and can go through the world that way. So you can like continuously go through the world over and over again and get completely different kind of answers, but they all fit the model. If that makes any sense.
And so I wonder whether comments like the one from Venkatesh on the birds with the dreamings, okay, is similar here. Okay, it's more like it's more about the result of their training. Okay, builds basically a neural network that will encode an internal model of the environment where the agent. That's why it's called world models. Okay, so maybe the dreamy part is because when we look into this neural network and we try to, you know, a neural network basically it's like a big matrix. It's bigger than the matrix. Okay, but basically we can slice it into images basically. Okay, and we have basically an array of numbers, and for each of these numbers we give a color, and that gives us an image. Okay, and so that's why we can see that several neural networks, especially the ones in computer vision, okay, they learn features of images. Okay, so they have an internal representation that looks like a blurry version of reality, and sometimes I see people labeling that as a dream. Okay, and I don't remember well the how it was in this research. Okay, but I wonder whether the title is not telling here that it's a world model, so it's internalization of the real world. Okay, so it would be different from the birds, that are actively dreaming. While they sleep, the brain is still doing something. Okay. What do you think, Venkatesh? It sounds different, no?
I think I'm getting at what you're saying. There's an aspect of dreaming that's kind of like much more focused on agency behavior. So for a bird that sings, singing is an agentful behavior for attracting other birds and so forth. And same thing, like the thing that reminds me of is if I play something like Tetris for a lot of time on a particular day, that night I'll actually literally dream of like Tetris blocks in my dreams. And I remember last year when I was like doing CAD after a really long time, and I was spending several days doing like CAD. I literally started dreaming about like shape rotations at night. So that I think is a type of dreaming that reinforces and it reinforces and anchors procedural memory. So you've learned a new skill and you have to rehearse it to lock it in long-term memory. Whereas I think there's another kind of dreaming that's this kind of like, I don't know, probabilistic exploration of a world you're in and not necessarily with agency. It's just like trying to like make the world model cohere. So it might be something along those two dimensions.
Yeah.
That's my speculation, pure speculation here.
Mm.
Yeah, I think that the world model comes into, we're just speculating, right? Coming into play for a bird practicing a song, and that like it can practice a song without actually making a sound because it has a model of how making sounds works, right? And then how, depending on how accurate that is, when the bird tries to do it for real, you get an answer that's, maybe close to reality or maybe not.
Yes. I'm aware of several approaches that actually follow that path, as Red explained. I just wanted to draw a quick parallel with something I presented a few weeks ago. In the I don't really like the choice of this 3D environment where we have a form that represents the internal state. Okay. In fact, there is a link to this research. Okay, I just realized now because I read that paper back then. Okay, and the focus is different. Okay, here for the rover, there are two aspects. There is the internal representation because it's trying to represent in some dimensional space the state, so that after we can apply deep learning. Okay, that's one aspect. Okay, so it's for self-diagnosis and stuff like that, but also for communication with other entities like other rovers, because two rovers have different sensors and they will have different internal representations, so different world models for the same concept. Okay, so if we have a cup, okay, different entities are likely to have different internal representation of that cup. Okay, still at some point we want them to be able to communicate about that shared topic. Okay, and so that's where basically I'm doing with that, and I just wanted to mention there is a link with this paper in particular.
Can stop sharing this somehow? Oh, there we go. The moral of the story is everyone should make a web page with interactive animations for their.
It's impressive, huh? That one is impressive, huh?
Someone did a lot of work on this. That's great.
The lead developer has moved to Tokyo. I think the year he published that. Okay, and I had a chance to meet him, and boom, we entered the COVID. So So his name is David, I think. Yes, David. And but he's a very good coder.
David Ha.
David Ha, yes.
Yeah.
Yeah.
Google
I think-
Brain in Tokyo, Japan.
Mayor, did you have something besides the mini rover link you shared?
Yes.
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 Oh, okay.
I have. Just a second. How does this work? I don't know if you recall this movie.
That's the Hokkaido factory.
Grocery packing warehouse in the southeast of
Just a
London.
second.
Folks have ordered their groceries online, and instead of people walking up and down the aisles of a traditional grocery store to pick up items, these little devices move more than 1 million items every day between them. Instead of trying to build machines that fit into a world designed for humans, this entire facility, the size of 7 football fields, is trying to build machines that fit into a.
So this is a very inspiring video which shows us how a complicated system is built out of agents, but these agents are actually robots, moving robots. And yes, it's a huge warehouse.
Humans, this entire hour, and they pass within 5 millimeters of each other when they move. So, how many robots are there in the hive? Well, that depends on how you count them.
What you're looking at behind me is the hive. We've got the grid, which is the metal structure. It's filled with products.
Okay, so I'll minimize that. So I find this, like I said, to be very, very inspiring in what a robotic system can look like in a controlled environment. And I don't know, some of the people in this forum have a vision that the outside world will look like that. Basically an uncontrolled environment, drones flying overhead, little robotic worms crawling on the floor, robotic ants cleaning up your house. So that is a link which I found to be very inspiring into a possible future. Now,
Do they describe it all? Do you remember like how much local peer-to-peer control there is versus like, is it one central super brain coordinating everything, or is it?
I do not
Just-
recall that they describe it, and you know, there's more than one system like this out there. It's a bit like the Kiva system. Okay, but it's not, because it's much more streamlined. There's an aesthetic here, okay, having to do with a task being very well defined. So it's pick and place. It's massively parallel pick and place with moving robotic elements.
It just looks amazingly efficient. Like just
Yes.
watching the video, it's like,
Yeah.
if you were trying to sell this to executives, they'd be like, yes, look at how efficient those robots are. I can tell just by looking.
Right.
So one of the interesting dynamics in this particular sector, since my advisor was one of the co-founders of Kiva, and I work with a company that competes with Ocado, it turns out that the market competition is shaping up based on one of two philosophies. Philosophy one is you try to build these sort of grocery type robots to fit into a workspace that's already been designed for humans. In that case, you end up with, all right, there's already shelving, there's already like walkways and stuff, and you want to like fit the robot in that environment. The other is clean sheet, go and redesign from scratch what an environment optimized for dedicated robots will look like. And one of the interesting things in the sector is it's not yet clear which one will win out in the long term, because there's examples of both out there. But in general, I think it's kind of interesting that you brought up like taking this vision outside of a controlled environment like a warehouse. So if you think of a spectrum with like a controlled design environment like this one, like something that's been designed specifically for this kind of robot and is also closed from interference. At the other extreme, you have completely wild like Mars that's not been designed for anything. You have to deal with whatever is out there. In between, you have the human built environment where it has been designed, but maybe not necessarily for your particular robot. Like, sidewalk robots still can take advantage of traffic rules and sidewalks and traffic crossings, but those were not designed with those robots in mind originally, right? So it's kind of somewhere in between. And it's somewhere in between open and closed as well. Like city urban environments are not exactly closed world, but they're not exactly open world either, because the defined rules define a lot more of the behavior than, say, the behavior in a rainforest or Mars.
Well, you can look at autonomous cars, but before autonomous cars, you can look at warning systems like Mobileye. Okay, so they somehow have to deal with just, a very small part of what is supposed to be standard, stripes painted on the roads. And that is a very, very difficult technical problem, which they've solved. Okay, so this is one very inspiring. The other one.
So sorry, just a quick comment on the communication. So as far as I remember, at least a few years ago, yeah, I think it's changing. I remember reading a long, I think, blog or post from the CTO of the Ocado, or the team who developed anyway, CTO of the system anyway. And he mentioned that there is centralized control, plus explicitly he used the term multi-agent system concepts for local coordination. Okay, so I guess the local coordination is when there are these holes basically with and so if two robots, maybe I'm not using the right terminology, but maybe there is some kind of bid system basically on who is going to get it. Okay, and there is local coordination not to bump into each other and basically to resolve. Beats, two robot beats on one, and there is communication delay. Okay, so if they start moving and bump into each other, it's bad. Okay, but so I think it's mainly centralized control and with multi-agent system concept for local coordination. I'll try to dig out the article. It was quite a few years ago.
It might have changed by now.
It might have changed because recently, I don't know who shared on Discord. Ocado is experimenting with 3D printed robots, okay, with arms, to basically to cover more scenarios into their warehouses. And so anyway, they are really betting on their technology, and it's moving forward.
Okay, so this other link inspires me in a different way. This is a dance contest. Dancing hexapods. Maybe I'll make this lower. The reason why this inspires me is because I would like the Yak Collective to do something like this. Okay, when I say like this, I mean it's exciting, it's visually compelling, it makes people feel like they can do it too, and it's not dry in a technical way. Okay, it's not, okay, we built a better operating system. It's, we have dancing robots. They're dancing to music. Okay, they look cool. Now, unfortunately, this contest is not on anymore, at least as far as I could find. Okay, but try to imagine a demo day generating a video like this.
It is the same chassis for all of the robots. Apparently, it looks like the same.
I don't think they're all dancing the same moves.
I don't know the hardware, the base hardware.
No, not quite. Well, maybe yes.
Yeah, they all look like the same robot with different paint jobs, but yeah, the programming looks different.
Because such kind of assumption makes a lot of things easier. Some other things more challenging. But in our recent discussions, we talk about maybe the value of focusing on software and on common software in particular. Okay? And basically to have maybe some applications running on an OS that can run on different
one
kind
has
of
extra actuator, the one with the head moving left and right.
Yes, but the base, it's the base remains. You know, it's like basically it's not the Roomba, but it's which one? The turtle boats. Okay, the turtle boat is there are several versions of it, and most of them are all based on the same base that looks like a big Roomba, basically the programmable Roomba.
Yeah, this one.
Oh yes, okay.
Perhaps.
This actually sheds some light on the distinction we made in the beginning on the kind of like two aspects of aesthetics. There's an aspect of aesthetics that's really function and evolutionary fitness in disguise. And there's an aspect that's just kind of like for fun in a way. It's like, surplus resources being used for fun kind of thing. And this contest shows both. Like if you take a behavior like dancing, there's a lot of exploitation of like the natural symmetries and sort of capabilities of particular design. And that's kind of like a functional thing. But stuff like, you just have more payload capacity. So you can just do something fun, like put a head on it with blinking lights. That kind of like is a more of a peacock tail kind of side of aesthetics. So yeah, just
it's not peacock tail. In other words, imagine your life when you're negotiating the streets of Los Angeles and people are walking by and robots are pushing by or ignoring people versus not every street corner, but actually every city block has dancing robots. Today you have on street corners, you have people sometimes dancing or playing music. Imagine that it was happening everywhere. It's a different world. But like I said, this inspires me for what I would like us to somehow generate as an output. Because this is an output that people who are not total technology geeks can appreciate. I'm not saying we should do a dance competition. I'm just putting it out. Okay, I can share another link here. So it's this one. I have to change my share. So the Godbot is an example of an alternative locomotion method. What's nice here is the entire design. This is the first type of aesthetics that Venkatesh was talking about. It's a very compact, integrated design, which is particularly suited for itself. Okay. So just a second. I guess this one.
This ball, it's no toy. It's a robot spy.
You have
It's
cameras
the
at his
guard
hand.
and it's currently being tested by the U.S. military. Round, remote controlled, and silent, GuardBot is billed as the only known spherical surveillance vehicle that can swim upstream. It runs on a battery-powered pendulum that swings back and forth, forcing the ball to roll about 3 to 6 miles an hour. They can be remote controlled via satellite from anywhere in the world. Invented by GuardBot Inc. in Connecticut, a basic model could go for $100,000. The demonstration model is 2 feet wide, but they're scalable. In fact, the company says the U.S. Army is interested in a tiny 5-inch version. Cameras on each side act as GuardBot's eyes. They also can be outfitted to detect explosives. New York City police have expressed interest in using it to prevent attacks like the deadly 2013.
A lot of interest.
Okay, so it's a ball. It rolls. The cameras are mounted on the sides. It's very nice engineering aesthetic. So that's why I put this link. Okay,
I don't know how much longer we want to go, but if people are willing to stay, there's one more I'd like to share kind of on the same theme. Like a sphere is a nice sort of platonic shape, and that's a particular direction to take, like aesthetics and beauty. And this, you guys have probably already seen this, but hold on just a sec. Pull that up before. The James Webb selfie. Can you guys see my screen?
Yeah.
Yeah.
This kind of really struck me as interesting for robots of all types. Like it was a functional thing of, it was collimating the hexagonal grid of mirrors, and it was doing so by taking a picture of one star and then lining it all up and overlapping the images. But in the process, it also took a selfie, and this is not just a selfie for a selfie's sake. Like all the Mars rover have been taking like Mastcam selfies, kind of like as a PR thing. But in this case, the selfie is kind of functional. It kind of tests some aspect of the alignment process, I guess. So this got me wondering about how do you get the robot to, or any kind of rover or robot, to build a self-image of itself in its environment and in relation to its environment. And this is something we take for granted. Like humans in general don't have a very good idea of what they look like. Like you don't know what your nose looks like. And even though we've had mirrors for millennia, when we look at a mirror, we kind of have left and right change, right? And there was actually an interesting Agatha Christie murder mystery that hinged on somebody imitating somebody else, where they learned the imitation behavior in a mirror. So when they actually tried it, they kind of like did it backwards, right? So building a self-image of yourself physically is a non-trivial thing. And it struck me that robots and rovers should probably have some aspect of this. So like, if you're injured or a wheel comes off or a leg is broken, yes, you could like have instruments and sensors for the whole thing, and maybe you could figure it out, but things can break in ways you've not modeled and not instrumented. So kind of a very general purpose approach is, how do you like use environmental feedback through selfies or mirrors or even reflection in a water pool or passing buildings to build up an image of what you look like to other creatures and to your environment? So anyway, thought this was inspiring for that reason. And same, like in this case, the telescope knows if it's healthy because it expects a very platonic set of like hexagonal grids as its self-identity, and it can match up to a platonic ideal very well, just like the spherical robot. And if it's off of the idealization, it'll know something has broken, right? Like this picture, you can easily tell if a mirror is broken. So
one thing that is interesting what you said, I think for humans, we have one word for many animals is to look at others of the same species. But it's true that for most planetary rovers, they don't have access to any others, so they don't even have any way to estimate their own shape.
Well, if you have one rover, it's kind of difficult. But if you have two, they can look at each other. And maybe do grooming, like cleaning off ticks or leaves or cockroaches.
There's a style of dance performance in India where one of the set piece routines they do is it's generally performed by women, but two women dancing sort of a mirror routine. Like one will be like doing the actions and the other will pretend to be a mirror. So, and humans have mirror neurons, right? So we are kind of like almost built for this. Like we mimic each other's emotions. You can do things like, and if you feel something is broken, like maybe I feel my shoulder is dislocated and I try to move my arm like this and I can't move it properly. And I can ask somebody else, hey, can you try to move your arm in a similar way? And if they can do it and I can't, that's kind of like a differential diagnosis that something is broken about my shoulder, right? So there's kind of like interesting possibilities in mirroring for self-image construction, which should probably be at an OS level. Like at an OS level, you should have a mental model that in some way reflects mirror neuron kind of like architecture.
Yeah, I'm not sure to understand the example with the shoulder, because if I ask you to move your ears, what does it say about me? I'm using ears on purpose because some people can't move their ears.
I can't move my ears, so that would immediately detect a difference between us, right?
And so a difference, but if I can't move my ears because usually I can, but for some reason now I can't.
Yeah.
So,
that's an abductive reasoning problem. So you have like some baseline assumptions about how similar are humans and how different are they. And from a Bayesian priors perspective, if I detect a difference, does that mean there's a difference between us, or is it a case where we should be identical, but the difference indicates that one of us is broken, right? So that's kind of interesting.
It's also, when we think about actuators and sensors, okay, I'm more on the basis that if we take two rovers, even identical, the internal model are likely to be different. Maybe not significantly different in terms of statistics, but they will be different. And so now, if I retake the example of the shoulder, some of my friends are active swimmers, okay? They are very flexible in the shoulder. They can do moves I just can't imagine to do, okay? And so that's why the differential diagnosis, I think it's valid, but in a very specific range. Okay, when we have a prior, as you say, okay, where we know, okay, that you and I will have basically the same kind of freedom on our shoulder. So yeah, we can use each other as a mirror, but it's something that we acquire over time that we can't assume correct without prior knowledge, right?
Actually, you could flip the thing and say you can use the ability to mirror as a way to build models of similarity. So maybe I have a diagnostic of like 15 things I can do, like raise my hand, jump with both feet in the air, something like that. And if any other robot can do the same 15 things that I have in my diagnostic set, I can assume it is fairly similar, both in terms of like structure and like life history and experiences it has had, that I can kind of like share mental models with it very well, right? On the other hand, if it fails, you can kind of conclude that maybe it's not similar enough and I should not make big assumptions. But on a more basic level, like this is the most sophisticated level of building mental models using other minds, I guess. But at the very simple level, I was thinking about like how self-revelation kind of like mechanisms are part of like design in very simple ways. Like the rovers and the James Webb Space Telescope have selfie cams, but cars have like a rear view mirror and two side mirrors. And this is like primitive technology way beyond, way before cameras. Now cameras are standard on cars. All modern cars have like multiple cameras and stuff. But for a long time, those three mirrors were it. And even now, like I was just thinking, got interested in optics and bought a bunch of like cheap optics things, including a bunch of like really cheap flat mirrors. And I was thinking I'll try and like install the mirrors on my rover build in a way that it acts as like diagnostic. Like that way you can have one camera that can maybe have 1 degree of freedom. Like maybe you mount it on a platform that can like pivot on one axis and look at different mirrors. But using mirrors and like optical reshaping, it can examine the condition of all its wheels, for example. So interesting possibilities are there with if you combine cameras and mirrors in interesting ways.
Mirrors get dirty, don't forget.
Yeah, like solar panels. Yeah, it's a hazard of things. But cameras break. Cameras are more complex components than mirrors, so there's that.
Yeah,
And
but
camera lenses get dirty, by the way. So this has been a problem with Tesla. Like I believe Tesla has had problems with its lower level cameras just getting dirty from driving.
yeah, but there are self-cleaning lens mechanisms, and because the camera is compact and powered, it's easier to clean.
Fair
But
enough.
a mirror, which is bigger and spread at the end of your legs or whatever, is more difficult.
Who says the mirror has to be unpowered?
No.
Connected to the servo.
Absolutely. But once you start doing all of that, you might as well put in another camera.
But speaking of mirrors in random space missions, you do have a mirror set up by the original Apollo missions on the moon. And even now, hobbyists like bounce lasers off it just to verify for themselves that the Apollo missions did happen. So I think mirrors and other like primitive tech should be kept in our sort of design vocabulary as things to use, because interesting possibilities are opened up when you use like simple elements like that. Because they're
I'm
passive.
realizing.
Yeah.
I was thinking about on my rover right now. I've got that new Oak D Lite, AI camera thing. It's got like 3 cameras in it. And it's a pretty tiny thing, but as far as all the components on my rover are concerned, it's like one of the heaviest. And so it would be very tempting to like have that be fixed and use mirrors to see other things. But like, it's actually pretty absurd that we got to a point where we can put all this compute on the camera. And now the camera got so big that back to the old days where cameras were actually really big and heavy.
That actually is a good consideration, because every camera is not just a piece of hardware. It adds demands on bandwidth, additional processing, and there's a whole software stack behind it. Whereas with a bunch of mirrors and a single camera, a mirror is just a heading direction. You point it in that direction, take a shot, and sort of interpret it later. But it puts software complexity further up in the inference path rather than the video path, but still. Every trade-off that you have gives you some more freedom to play with.
It seems to me the discussion is about self-diagnosis, and for rover and an autonomous system, that's so especially the way something like the Webb telescope. It's a fantastic topic actually, but I wonder, are there two sides of a coin here, where we have external diagnosis or diagnosis from outside, and internal diagnosis, so diagnosis from inside, and do we see any value in having both, or is there a way to have only one and have enough information? The way I'm talking about that is because to have internal diagnosis, we can close our eyes and we can concentrate on part of our body, okay, and we can infer quite a few things about, I feel good, or I have pain in my foot or something like that. Or we can also look at the foot and we see, it's red, and I feel the pain, okay? And so it seems there is a correlation between how it looks and how it feels inside. But we also know cases where, we got bumped somewhere and there is nothing visible, okay? But we know we are in pain, okay? And so on this topic of diagnosis, do we need both? Or because external diagnosis means we have an apparatus to look from outside, okay? And so this is where discussions with mirrors and so on come. But to me, a mirror is something so sensitive that if we talk about mechanics, okay, we're talking about dropping our rovers from the 3rd floor of a building to see whether it will be able to land on Mars, basically. Okay. If we want to align mirrors after that, I think maybe we have quite a few patents to fill after that. Okay. I wonder whether maybe from the OS perspective, maybe the internal diagnosis is maybe much more valuable and robust.
I think you will need both because they kind of serve different but overlapping functions. Like, for example, I'm thinking of the Perseverance rover. You've got like two ways to measure a wheel rotational velocity. One, you can put like an optical encoder on the motor shaft itself. That's your proprioceptive type strategy. It's like sense internally how fast are my wheels spinning. But there are aspects of a spinning wheel, like slippage and like loose gravel that you cannot get at. So the both rovers actually encoded a different mechanism for like capturing wheel rotation, which is the tire tread pattern. It leaves a trail behind. And I believe Curiosity actually encoded like a bit pattern in the trail track for fun. And Perseverance just uses like a zigzag pattern. But the point is, you can actually look at the trail you leave behind in the mud and get an absolute measure of like your rotation. So I think for absolute referencing, you generally need external. This is also true for like take your inner ear canals. Like that's a standard like 3-axis orientational mechanism. But if you spin around rapidly or are otherwise like disturbed a lot, your inner ear can like get miscalibrated. Like if you have an inner ear infection, suddenly your sense of balance can go off. So you kind of need visual calibration against external landmarks to say, all right, is my sense of orientation of up and down from inner ear canals actually accurate? So I think external, you can have limited capabilities, but you do need some to drive calibration and referencing. But internal can kind of like carry the bulk of the weight most of the time, I think.
Yeah, you know what? The how you present that? That's very interesting because if we build an internal state, okay, the thing I'm trying to do, okay, internal state, we build it. It's really inward, okay, and so there is no guarantee that it's aligned with what happens in the environment. Okay, so by align I mean in terms of symbol. Okay, is that I build a symbol. Okay, let's say the letter X. Letter X means a cup. Okay, but is it aligned with what is the environment? And the only way for that is to look outside, basically. Okay, and if I push that. Then for communication with other rovers, then this is where we start talking. Okay.
There's a very interesting experiment you can do easily on yourself to see the importance of this. So I think one of my personal trainers or somebody showed it to me. If you stand up in the middle of a room and close your eyes facing one wall, and then just close your eyes and for like 60 seconds on a timer, just march in place, like up, down, up, down, up, down. And your goal is to like stay pointed in the same direction. You open your eyes, you will generally find you've rotated between 60 to 90 degrees. Like our internal orientation sense in marching in place without visual cues goes completely miscalibrated very quickly. Another example is try balancing on one foot with your eyes closed versus your eyes open. You will find it far harder to do it with your eyes closed because we use visual for like the top of your head level of angle sensing. Whereas if you're trying to balance on one foot with your eyes closed, it becomes much harder because only proprioception and your lower calf muscles are available as feedback signals to do the balancing. So both are very good illustrations of like why you need to triangulate internal and external sort of state sensing.
Very interesting. That makes me think about. I'm reading a couple books on ROS, okay, by the ROS designers, and they have whole sections about basically how to initialize the system. Okay, that they use a total board, by the way. Okay, in the book I'm reading right now. And we write an application, okay, and we build into the rover a map, okay, of where we want it to move. And after, the problem is to tell the software, okay, where are you on the map? when you boot up. Okay. And that makes me think about this example about standing in front of a wall and we just move. Okay, so we create noise basically, and when we reopen, when we boot, then we don't really know where we don't really know. There is some ambiguity of where we are. Okay, and so how to align reality with the internal belief of where we are.
And
Sorry,
noise is exactly right. This is dead reckoning. Like in a very basic sense, if you take an accelerometer output and you integrate it twice for position, you're integrating noise. If to the extent the accelerometer is noisy, you're integrating noise, and the longer you let it run, the worse the dead reckoning will get. So that's why typically dead reckoning of even simple position is recalibrated against, like stars or some other external reference periodically. Otherwise, it'll go completely off.
Yes.
You can, I think, generalize that to in some sort of very fundamental information theoretic way. Like take the states you want to sense, how much noise is in the internal sensing channel for each, and what's the sort of external ground truth you can sort of tie it to. And you can probably work out like some Shannon entropy type thing for how often do you have to recalibrate for it to reset. So sounds like something somebody would have already worked on.
But I don't have any reference right now, but in control theory, there is quite some work on that. The control theory is mainly about feedback loops, okay? But it's not starting in a void, basically. It needs the proper initial conditions, okay?
Yep.
Because the feedback loop can diverge, okay? If we put it, if the initial conditions are not correct, it can get out. It can, what would be a more generic way to say diverge, unstable. It's unstable basically. Okay. So, last year, I'm not sure it's the right terminology, but I am using often, situation or context awareness. Okay, or these are concrete aspects of situation awareness. Okay, so. Sometimes we sleep, we wake up, and where am I, basically, okay? And we need to align that. And so, with any artificial system, there is this problem. Is this called dead reckoning?
Dead reckoning is the term in navigation, but in other contexts, you have like time is another example. Like when you wake up, how do you know what time it is? So the body has an internal, I think that's called free running or something like that. Free running is the term for internal body clock integration. Like literally how you know how long has passed when you're awake is you're kind of like integrating some sort of body clock. And when sunset or sunrise or some external cue comes in, you kind of reset. But when you're asleep, it's actually really difficult. The only indication you have of what time it is how recovered you feel. And like sometimes when I wake up in the middle of the night, I think it's 5 a.m., but it's really just 3 a.m. So the error for like guessing time when you accidentally wake up in the middle of night is like plus or minus 2-3 hours in my case. I don't know what it is with you guys. So yeah, every specific kind of state estimation problem has its sort of integration and free running or dead reckoning error rate and its requirements for recalibration. Time is really bad. Like I think people who stayed in that Biosphere 2, was it the isolation thing experiment where they lived without external cues? Their bodies reverted, I believe, to a natural cycle that was not 24 hours. So they got out of sync with the normal day cycle by either, I think it was smaller. I think they ended up with like a 22 or 23 hour cycle instead of 24 because the human internal clock, I think it's adapted to ancient like evolutionary period when the earth was actually rotating faster or something like that. So I forget the exact explanation, but yeah, free running human body clocks are shorter than when you get to reset it with sunrise and sunset.
All right, I'm gonna drop off.
Oh yes, we already an hour and a half. Huh? Good night, Rita, and see you next week.
Yep.
Next week we talk about. Oh yeah, okay. Rita has shared something about the strawman. Okay. And so, and you too, Venkatesh, right?
Yeah, I posted some comments. So yeah, next week is a strawman discussion.
And so I also have a document that I wrote the same day of our meeting when we talked about the strawman. So apparently we're going to have an interesting discussion next week.
Yeah.
Yeah.
Competition of 3 strawmen knock each other to pieces.
Oh, but they are related. They are related.
Yeah.
So it's all right. Shall we stop now, because it starts to be pretty late for you too, Venk, right? Yes.
Yep.
So
All right.
thank you.
This was a fun discussion. We should do it periodically. It's good to share links and talk about them.
Indeed, yes.
All right.
Thank you. Good night. Bye bye.
See you guys. Bye.
Thank you.